capacitor charging, let's say. You could be charging or discharging. You see, so imagine you have a RC, back to RC circuits, right? You have RC. So imagine these are circular plates like this. Or it could be square shape, it doesn't really matter. So now, as it's charging, charge is building up on this. The electrical field is getting stronger, right? So then you have no current though, actually. You have no actual current in the wire. I mean, in the capacitor. So you have B dotted into DL, mu 0, E0, d phi d phi E dt. So here, there is no I enclosed. There is no conduction current. Okay, so then what's going to happen is it's going to create, the thing is, if the electric field is increasing, if it's increasing over time, it's going to act as if there is current flowing that way. And it's going to create a B field like this around the capacitor, going around the back, coming. And it's also going to create a B field inside the capacitor. You see? So here's the capacitor plates. Let's see if there's good pictures of that. B field created inside capacitor. Capacitor due to changing E field. Magnetic field in a time-dependent capacitor. Ooh, Princeton University. Oh, it's a lot of the stuff we covered today. Look at that. R over R squared, 1 over R, right? So you guys are up there. Oh, law of cosines. Right? You guys should be able to understand most of this stuff. The effects of a current in the capacitor. You see? Oh man, this is exactly what we're talking about. Direct calculation of the radial current. Magnetic field inside the capacitor. Oh man, we hit it bullseye. Complete bullseye. Save this article. Magnetic field inside a narrow gap capacitor via the Biot-Savart law. Ah, they're treating it as a awesome, man. Awesome, awesome. Okay, so let's see if there's some images for that. Ah, there it is. That's a nice image. You see that? Why is it when you click on a good picture and then it takes you to a weird website? I just click here and it takes you to me completely. Okay, so here's there's current. There, you see there's conduction current here outside in the wire. Then it comes, builds up charge in here, and then the E field here starts increasing. And it acts as if it mimics the same effects as a conduction current. It creates magnetism inside the capacitor, inside and outside. See, that's a pretty good picture. You see that. It's a nice one too. Ah, okay, okay. No, this is parallel. This is square plates right here. So it doesn't matter the shape of the plate. You see here, same idea. Okay, so let's say we were to give this a certain radius, the plates 0.1 meters. So then we could say, let's give it a certain capacitance, 2 microfarads. And let's say the resistor is 30 kilo ohms. We can say this is 20 volts. What is the displacement current at t equals to 10 milliseconds after connecting the battery? And then B, find the B field on R equal to 0.05 and 0.15 meters from center of capacitor. So once you find the displacement current, which is this portion, then it's easy to do the magnetic field. So the displacement current is going to be E0 times d by dt, and then the phi E is EA, right? Because the electrical field is uniform everywhere inside, right? And so it's just going to be EA. And then E is going to be, oh, so A is going to come out of the integral. A comes out, E0, and then E is going to be the voltage divided by the distance between the plates, D, right? So the EA, E0, D, dt, voltage between the plates, and then over D. So D also comes out, A, E0 over D. And then what's the equation for the voltage across a capacitor in a charging RC circuit? We have that from chapter 28, right? VB 1 minus e to the minus t over tau. Right, so that's the voltage across a capacitor in a charging RC circuit. So then we take the derivative of that, of the charging, the voltage of the capacitor in the charging RC circuit. Right, okay, so now that gives you the displacement current. So A0 over D actually happens to be the capacitance of the capacitor, which is given, right? So then I'm going to just replace this by C. C, VB will come out, CVB, right? And now the derivative of this is going to come out what? The derivative of 1 is 0, and the negative 1 over tau will come out. So 1 over tau, e to the minus t over tau. CVB, and then tau is just equal to RC. the time constant of the RC circuit is just RC. So the C also cancels again. So a lot of things just canceled. And now I could calculate the displacement current, the voltage of the battery, 20 volts over R, which is 30 kilo ohms. And then e to the minus, and then t is going to be what, 10 milliseconds. 10 millisecond, right? And tau is going to be the product of R and C, right? What was R? So R and C, that's tau. So 30 times 2 is 60. Right, 30 times 2. And then kilo times micro is also a milli, right? Yeah, that's a millisecond. So the time constant is 60 milliseconds, and I want to find out the displacement current at 10 milliseconds. So then that's it, really. This cancels this. 0 cancels 0. Okay. So then you just do 20 over 30 divided by 30 times 1/6 times, oh, you know what, let's start with 1/6. 1 divided by 6 equals negative, then raise e to that power, then 20 over 30. So then it's going to be 0.564, and then 1 over kilo gives you milliamps. All right, so I didn't even use the kilo. So then that's a milliamp. Yep, so that's the displacement current at that time. Right, now if you want to find the B field inside of the capacitor at the 0.05, then you use this equation again. V0I displacement over 2 pi r squared r. Now notice in this case, the displacement current came out to be a pretty big number. In other words, it wasn't something like 10 to the minus 18 amps, 10 to the minus 19 amps. Because of the, I don't know what happened. Oh, because the capacitance of it is incorporated into the E0. You see, the E0A, E0 over D is already the capacitance. So that was one of the main reasons why displacement current comes out small, because of the E0. Well, that one already engulfed and became C. And then the C and the C canceled, and actually the C just canceled, and the displacement current actually acted very similar to the conduction current in the wire. So that's really weird that you have such a strong displacement current and very similar to the conduction current, even though there's no actual current in the capacitor. You see, that's the surprising thing of that. So now you can just put 2 times 10 to the minus 7 displacement current milli over 0.1 squared times 0.05. And then you're going to get whatever, just put that all in. And then for the outside, I'm not going to calculate it because it's just straightforward. And then for the outside, you're just going to do mu0 I displacement current over 2 pi r. And then R is the 0.15. So pretty straightforward there.